Good afternoon, good evening, good night, wherever you are. So today I want to talk about FaRM. This is a paper from 2015, so it's a little bit more of a recent paper, and it's really a research paper. And the topic of the research paper is trying to explore some ideas and technologies to get high performance transactions. And with it, high performance, just to make sure that we're on the, sort of roughly what we're looking for. High performance for them means they're getting 140 million transactions per second on this, TATP benchmark using 90 machines. And so, whether this number is impressive, of course, depends on like other numbers, And so, anybody remember like how many transactions per second Spanner could do? Anybody? So if we remember in the paper, there was sort of an transaction there, took about, depending on what you did, 10 to 100 milliseconds. So, 10 to 100 transactions per second. And so the number of transactions that FaRM can do is in a completely different order of magnitude. And that partly is because they're completely different systems. Spanner tries to do synchronous geo-replication across the world. And FaRM actually, everything runs in a single data center. And so the applications that are being targeted by FaRM and Spanner are quite different. Spanner is targeting applications that cannot tolerate the crash of the data center, like the F1 ad serving database, while Spanner is FaRM is much more targeting sort of like if you were using MySQL or some other sort of database system, and you want much more high performance transactions, then FaRM is sort of a possible design or a possible alternative. They do provide strict serializability, which is similar to the external consistency that Spanner offered. And so the whole goal is to get high performance. So there's a number of ideas that go into achieving high performance. One, they shard. That's probably the main sort of standard technique that they use that is going to give us performance. For example, if different records are on different shards and the transactions touch the different shards, then these transactions can just run in parallel. And so if you have 90 machines, you get 90 times the performance of a single machine. So sharding is sort of the starting point, but then they go much further. So they use non-volatile DRAM, and this is to avoid the bottleneck of having to write to stable storage devices. So in their design, you don't actually have to write in the critical path to an SSD or a disk. And so they avoid the whole cost of doing so, and which can be quite expensive. And so, for example, if you think about your implementations of Raft, they store or make data persistent, and typically making something persistent on a stable storage device is in the order of hundreds of milliseconds, hundreds of a few milliseconds, to tens of milliseconds to 10 milliseconds if you're actually using a magnetic disk. But an SSD, sort of a millisecond. And so, given the time frame they operate, that would be too costly. So they use something what they call non-volatile DRAM. This we'll talk about in a second. So that gets us rid of sort of the storage access cost. And so the next two bottlenecks they address is CPU bottlenecks and network bottlenecks. And for that, they use a technique called kernel bypass, which basically avoids the operating system to talk to the network card. And then they use network cards that have a special feature called RDMA that allows the card to read and write memory from a remote server without actually having to interrupt that remote server. And so this gives us really low latency network access to a remote server or to remote memory. And this is where partially where the name FaRM comes from. The R stands for remote, M for memory, and the F is for fast. So those are the sort of the technologies they use. And then to be able to really exploit these technologies, this drives them to a design that uses optimistic concurrency control, or OCC, the short version of this. So optimistic and in contrast to many of the designs that we've seen so far, where they use what was typically called pessimistic concurrency control schemes. And pessimistic control schemes basically acquire locks on the objects that are being touched by the transaction. So when they get to the commit time, they own all the locks for all the relevant objects and just go ahead and commit. While with optimistic concurrency control, you don't actually acquire locks, and particularly in FaRM, you don't require locks on the read transactions. And when you then go commit, you actually have to validate that you you have read the most recent objects. And if so, you can commit, and if you're not, you have to abort and maybe try again. And the reason they use optimistic concurrency control, as we'll see in a second, is really driven by the fact that they want to use RDMA. Okay, so then the final comment I want to make on this is sort of an overview. This is really a research prototype. So unlike Spanner, which is a deployed system that is being in active use, FaRM is really a product of the research arm of Microsoft Research, trying to explore new ideas, to see if one can achieve higher or really high performance transaction systems. And this is just a very active research. People would just love to have the power of transactions, but also the performance. Okay, so that's sort of a short introduction. Any questions so far? Okay, let's talk a little bit about the setup. For FaRM. And so there's basically 90 machines. Many of these guys, they're connected by a high-speed data center network. And to see a particular one, I'm just going to draw that as a single line. Of course, it's a switched network internally, and basically shards. The data is sharded across these different machines, and the level of sharding happens at something that's called the region. So region is 2 gigabyte, and those regions are sharded across the different networks and the different machines. The regions live in memory, so this is just DRAM, and not for example, on the disk. And so basically, the total data set of your database actually has to fit in the joint DRAMs of the machine that you're using. So if your data set is larger than your current set of machines, you have to buy more machines to get more DRAM so they can actually fit. And again, the reason why they want to use DRAM is because they don't want to be bottlenecked by the performance of storage devices. And so, of course, a machine can fail, and if a machine fails, it loses a DRAM, and so therefore they use replication. And so they replicate regions across multiple machines. One machine is the primary for a region, and the same region might be replicated on another machine, which is then a backup. So they use primary backup for replication. And so this is region 1. region 2, the backup might be on the same machine as the primary for backup for region 2. And here, we have the primary of region 2. And so this deals, so if one machine has a kernel panic, or some device goes bad, or just crashes for some other reason, then there's a second machine that actually has a copy of the data and just could proceed from there. Of course, then we need some way of keeping track of the mapping from regions to primaries and backups, and so they use a configuration manager, a CM that sits on the side, and the CM itself actually is coupled with a system that we've seen before, Zookeeper. And it's really the Zookeeper and the configuration manager that keep track of the mapping from region number to the primary and whatever the backups for every region. Okay. Now, there's one serious problem, of course, here. I talked about we have primary backup replication, great. So we have faults, then one machine can fail, another machine can take over. Except the one sort of tricky case that this scheme can't handle so far is when there's a correlated failure. For example, there's a power failure of the data center, and all machines go down. And to handle that case, basically the DRAM sits on a UPS, where every machine sits on an uninterruptible power supply. So we're going to draw this as like a big battery that sits on the side. And the battery basically, or the UPS, provides enough energy that if there's a global power failure, the machine can keep running for a little time, and in that little time, the machine can actually store, the FaRM will actually store the data on SSDs. So basically, it just flushes, the content of its memory, all the regions, all the transaction state, all the logs for the transactions. It actually flushes it to an SSD. So if there's a complete power failure of the whole data center, the data center at some point will come back up, and they can load, the memory contents of the machines from the SSD and start basically running again. And so this is basically the only place where the SSDs are being used to deal with a correlated failure of many machines in the data center. Any questions so far? Okay, now let me say a little bit about the software. So in the regions, so we have a region here. In these regions, objects live. So you can just think about it, an array, a region as an array of bytes, 2 gigabytes of bytes, and in the array of bytes, objects live. And objects have a unique identifier, an OID. And the OID of an object is nothing else than its region number, its tuple of the region number, and then the address within that region. Associated with every object, there's a little bit of metadata for that particular object. And in particular, for the object header contains a 64-bit number. And the number is basically a version number in the bottom 63, and then a lock bit, as we'll see, in the top bit, in the high order bit. So every object has this 64-bit number. I'm just going to refer to it as a version number, and then we'll see it plays an important role in the optimistic concurrency control. The way applications use the system, let me say a little bit about that. So what's sort of the application programmer interface? So the API is your started transaction, then you read some objects. So there's a read a call, and the read call takes an OID as an argument. The application then, for example, can manipulate, change the field in the object, whatever, add one to it, and then at some point, write the object, update the object itself using a write call, and then commit it using sort of txtend commit. It might also be the case that the transaction needs to abort, or because of the optimix concurrency control, and in that case, the application will typically just retry the transaction. And so in the transaction, the way it showed the transaction here, there's only one object manipulated, but the transaction can manipulate many objects. Those objects could live in different regions. And so they have to have some plan, as we'll see, for running some two-phase commit-like protocol to do atomic operations across objects living in different regions. Any sort of questions about the API and the setup?
Sorry, the address OID, it is the address in the machine itself?
Yeah, it's just the offset within that region. Okay. Because regions can move, correct? If they re-replicate it, or the configuration manager redesigns the mapping, the actual address where the object lives might change. So it's just a region number plus an offset. So if I'm a little bit better here, I should set an offset.
Sorry, I have another question.
Yeah.
Kind of related to that. What was the design choice or design thinking behind making a global address space?
To have everything in DRAM. I'm not sure that answers your question, but the whole goal of them is to actually run the transactions on an in-memory database. So there's this whole trend of set of databases where all the data is always in memory. It's called in-memory databases, driven by the fact that DRAM is reasonably cheap, and so that would allow you to basically run transactions without actually having to go to persistent storage. And they're basically jumping on that train of in-memory databases.
I see, and that requires like a global address space that they all share.
The address space is per machine, right? Every machine has its own address space from 0 to whatever, and the objects are really the global numbers or global names.
Thank you.
Okay, good. So let's talk. So far, I think we basically sort of established that they sort of gotten the stable storage devices out of the way, and so there's no bottleneck for reading and writing storage devices because they're basically not using them, other than in this one exceptional case when the power fails. And so the next set of things they focus on is trying to reduce CPU utilization, or try to be very efficient with the CPU and be very efficient with the network. And there's two key ideas here that are pretty well known. So the first one is kernel bypass. And the story of that is reasonably simple. So we have FaRM that runs as a user level process on top of Windows, the Windows operating system. So here's the operating system. So let me move it a little bit on the side. So here's the operating system. And the operating system, of course, has all the features for scheduling processes, virtual memory, standard operating system. And it also has drivers for hardware devices. And like one of the hardware devices is a network interface card. And typically, the OS has a driver inside of it that programs the network interface card. So it reads and writes registers on the network interface card to basically send a packet or to reconfigure the network interface card, et cetera, et cetera. And so the typical way that applications interact with the network card is they make system calls to the kernel and ask the kernel to basically send a packet. And that involves the operating system, involves the TCP stack, the network stack, and tends to be quite expensive. And so they want to avoid this this overhead of going and entering the kernel, running TCP, et cetera. And the way they do that is something there's a technique called a kernel bypass. And if the network card, there's a sort of a collaboration between the network card and the operating system. And basically what it does is that the queues that the network interface has, so here's some set of queues, for example, send queue and a receive queue. Those queues are basically directly mapped or into the address space of the application. So the application can ask, operating system, please, take some queues that the NIC has and map them into the address space of the application. And so you can just think about this as this queue. This basically is directly accessible from the user level application. So the user level application, can basically now read and write, commands or packets into the network interface card without actually having to involve the operating system at all. And so this cuts the whole operating system out of the picture and improves performance considerably. In the case of FaRM, they also don't want to use interrupts. One way of delivering a packet, correct, is the packet comes in, the network interface card delivers an interrupt to the operating system then alerts the application that a packet has arrived. And in FaRM, they try to avoid that cost. And the way they avoid that cost is basically they pull the receive queue. So there's basically a user level thread, that sits in the FaRM application, and it basically does nothing else than sort of reading the receive queue to see if actually a packet is available. And so that requires no need of operating, so that avoids the use of interrupts and at the cost of basically having a polling thread that's sits there doing nothing else than polling. In FaRM, it turns out this thread actually switches back and forth between running some application code and polling the NIC. So that's sort of kernel bypass. And this is reasonable standard. Some people may, some of you may be familiar with DBTK, which is the data plane development kit, which is a development kit to basically leverage kernel bypass. So it's a reasonable standard thing, and it's available on many operating systems. So then the next sort of piece of technology that I use is a little bit also well known, is widely standardized. Many network cards support it, or more high-end network cards support it, and that is something that's called RDMA, which stands for remote direct memory access. And the basic idea is that this requires NICs that actually understand RDMA. And so here we have a cable, here we have NIC on the other side, the operating system maybe sitting on top of it. Here we have FaRM. And basically, the application on this site, on the sender side, can basically put a particular packet into the send queue and send an RDMA packet. So basically, somewhere there's a bit in the header of the packet saying like, "Hey, I'm an RDMA packet." And then the NIC will send it over to the NIC, the destination NIC. The destination NIC sees that this is a special packet, an RDMA packet, and looks at the instruction that goes along with the RDMA packet. And so the instruction might be read a particular memory location or write a particular memory location. So here it is. So for example, let's say it's a read operation. And the read operation basically takes an address, and it allows the NIC to basically read that address straight out of memory, out of RAM. So for example, let's say we have our region, with objects in it, and the sending FaRM application can just say, okay, I want to read this particular address, which may correspond to this address of this object O, and we'll send an RDMA packet to the NIC on the other side. The NIC sees that there's an RDMA packet, and basically reads from memory the value stored at that particular location, and sends them straight back to the source. And what is cool about this technology is that the NIC can do this without actually interrupting or interfering with the server at all. It doesn't have to generate an interrupt. It doesn't have to run any code on the processors that run the operating system in the application. Instead, the NIC just has firmware that runs, executes those instructions and loads, the value stored at those the requested memory addresses, straight into a response packet and sends the response packet back. And then, of course, on the receiving side, that will show up in the receive queue. And so FaRM, at some point, will pull the receive queue and see actually, the result of that RDMA. This particular version that I'm describing here, the paper refers to as one-sided RDMA. And that typically refers in the paper to read operations. Yeah, go ahead.
Sorry, Professor. Can you repeat how the polling of the like NIC queues works on a client, or on like
There's almost nothing to it. The client just has a thread that reads a particular memory location, and which indicates whether a packet has arrived or not. And when the NIC receives a packet, it sticks it in the receive queue, and as a side of setting it in the receive queue, the flag, the bit, turns into a 1, and the application knows, oh yeah, there's a packet there.
Is it a specific thread that that polls all, like?
Yeah, in their system, they have specific threads that actually are dedicated to polling the queues.
Okay. Thanks.
So, sorry, I'm a little confused here. So does the NIC cooperate with the system, or is it regularly doing a job, like as in any regular NIC?
This is not a whatever your standard NIC, right? There's a NIC that supports both kernel bypass and remote directory access and RDMA. And typically for a NIC to support a kernel bypass, it means it has to have multiple receive and send queues, and it just gives a pair of the send and receive queues to an application. And it cannot, like, of course, you can't have a send and receive queue for every process running on your machine. So typically there are like 16 of them or 32 of them, and give some of them to a particular, or the OS basically allows some applications to own basically a send and receive queue.
I see. Thanks so much.
And that also means there's some specific support for DMA and make that all work out. So, so it requires a NIC that is reasonably sophisticated, although it's reasonable standard these days. Okay, so that's one-sided RDMA. They also use RDMA to do writes and to actually implement RPC. And so there's they typically call this write RDMA in the paper. And it's basically the same thing, except the sender can put in the RDMA packet saying like, oh, this is a write operation, and write the following bytes to a particular address. And the paper uses two places or two things where writes are actually going to. Objects are never really written directly with RDMA, but there's two other data structures that are being written with write RDMAs. One is a log, and we'll see the role of the log later. And this is like related for the transactions, so it has commit records, locking records, et cetera. And so if the source wants to append a lock record to this particular log, it can just do a write RDMA, and then the receiving NIC will just add the new entry in the log to the specified location. Okay. And so that means like the sender, and so there's one of these queues and one of these logs is per sender receiver pair, so that the sender actually can manage and know what the beginning and the end of the log are. Then, in addition to that, there are message queues, and also one per pair. And these are basically used to implement RPCs. So if you want to do a remote procedure call, the client, the sender makes a write RDMA packet, writes the data, the message basically into the remote message queue. There's a thread sitting on the destination site that is basically polling that message queue or polling all the message queues. If it sees a message, it processes the message and can then send a response back using a write RDMA. And this turns out to be cheaper. Implementing root procedure calls using RDMA, it turns out to be cheaper than basically using sort of a standard RPC package that sends just package using a regular NIC, but without RDMA, and has a thread on the other side that responds. Okay.
So is there any validation step here to make sure that you're only writing to a region of memory that's like expressly allowed for RDMA? So like you don't write onto application memory or something? Yeah,
so there's all kinds of, this is sort of the high level idea. There's all kinds of details here. So when you sort of set up one of these RDMA, in order to do these one-sided RDMAs or write RDMAs, you first have to do a connection setup. So there's a negotiation step between the sender and the receiver to set up basically like it's almost like a TCP channel, except RDMA doesn't use TCP, but it sets up a connection-oriented, reliable, ordered channel. And sort of the security checks and access control checks are happening at the point of the setup.
So would you have to do that between every pair of machines?
Yes.
So that would become really costly to add like one machine to a large cluster, right?
We have n-square RDMA connections. And otherwise you would have n-square TCP connections. And not clear, there's a major difference there.
So just to clarify, so the message and the logs, basically they both sit also in memory. They just sit in different places than where the objects sit.
Yeah, exactly. So if you do, so this is sort of here on the right, is sort of a picture of the memory layout of the FaRM process. There's a region table or an object table. Well, there's regions in the memory of the server. These regions have objects in them. And in addition to the regions, there are message queues and there are logs.
I see. And also for the NIC to support the direct access from memory. So since here we don't have any software involved, since the NIC can directly access the memory without even notifying the application or the OS, shouldn't be some coordination on the hardware level or at least some support also from the processor to this feature?
Yeah, so there's basically, the NIC can read or write cache lines atomically, and so to support this, there is an interface, to the memory system between the NIC, and that it has to be carefully set up, between the OS and when the connection setup is done.
I see. Thank you.
Sorry, the write to RDMA on the right side that is in red.
Yep.
What happens there?
So the sender, the left machine, can do a write RDMA, which basically sends a write RDMA packet, to the right side, the destination, and the NIC, sees that this is a write RDMA packet, and will write the content that came in over the network to the address that's specified in the write RDMA command.
But that would be just.
And so there's a remote machine can just write the memory location, a set of addresses on the destination machine without actually having the server, being involved, other than doing setup, of course.
Yeah, thank you.
So quick question. So the queue in the NIC is only used for read RDMA. It's like the writes directly to memory and the receiver.
Yeah, okay, so they're on the right RDMA, as you maybe noticed in the paper, there can be an acknowledgement coming back. If the sender does a write RDMA, it can wait from an acknowledgement from the receiving NIC that it actually indeed performed the write RDMA.
Okay, thanks.
And it will play an important role. Any more questions about this part? This is sort of a cool piece of technology, that has come into existence quite widespread in the last decade, and basically they want to leverage it because it allows them to get very, there's nothing, the latency to actually do one of these one-sided RDMAs is about 5 microseconds. So very low latency. Much faster, correct, than, for example, reading or writing a disk, and not much slower, slower than writing your own memory, but pretty fast. Because it allows you to do, if it's 1 microsecond, you could do 1 million packets per second, which is pretty impressive. Okay. So this so far basically standard technology, right? Cutting edge, but standard. So the real challenge that this sort of paper addresses is actually how to use RDMA, both write RDMA and one-sided RDMA to actually doing transactions. So the challenge that this paper addresses transactions using RDMA. And to sort of see that this is a challenge, we sort of have to think a little bit about all the protocols that we've seen so far. So sort of protocols for transactions, two-phase commit, etc. All of those protocols have required sort of server-side participation. And so, for example, what I mean with that is, a client sends a request, or the transaction coordinator sends a request to one of the participants, for example, to require a lock on a particular object, and just waits, on the server or on the receiver until the lock actually becomes available, or runs, the server runs some validation step, to see if the transaction can be committed or not. And so in all those cases, basically, if you have sort of server-side participation, that means that you have to run code on the server. And that is sort of counter to what RDMA gives you, right? RDMA actually doesn't really provide you with the ability to run code on the server, and so the designers or the authors of this paper have to come up with sort of protocols that allow you to implement like two-phase commit and transactions in general to without actually or trying to reduce server-side participation, so that they can at least do some part of the operations using RDMA, and some using remote procedure calls, as traditional would do in a traditional designs that we've seen in the last couple of weeks. And so that's sort of the central challenge in this paper. And this pushes them in this direction, and to sort of solve that problem. The high-level strategy that they use is optimistic concurrency control. And really where this shines for them is on the read operations. Because basically the basic plan is we're going to read objects that are part of a transaction without acquiring locks. For example, acquiring locks, that would mean interrupting maybe the server. The server has to do some work, and then maybe you block the client until actually the lock is available, and then return the object. And that is not really suitable, or it messes up nicely with or lines up nicely with RDMA. And so they're going to go to an optimistic scheme where basically reading objects is not going to require any locks at all. You just can fetch an object and start using it. And as we'll see, of course, you need to have some mechanism to discover whether you're reading an old version or a new version. And this is where the version numbers are going to play an important role. So when you read an object in FaRM, you get the object back, and you get also the version number back for that object. And then the basic idea is that at the point of commit, we're going to do a validation step to check that the objects that you've read at the beginning of the transaction are actually haven't been modified. And so during the validation step, we're basically going to check for conflict. And the conflict is basically if the version number has been incremented since the coordinator actually read the object. So if the version numbers are different, then the transaction is aborted. And if they're the same or still the same, then basically means that no other transaction actually modified the transaction, the object, and then we can actually go ahead and commit. And of course, in the case of abort, what typically will happen is that the client, will maybe run the whole transaction again, perhaps waiting for a little while before actually doing it for some random period of time. So that's the basic plan, right? So this is just this optimistic scheme so that reads can completely exploit RDMA. And as we'll see, in fact, reads won't require any state changes on the servers at all. And so this is basically sort of the basic idea behind figure 4. Except as we'll see in a second, there's quite a bit of more complications to it. And so this, again, sort of I think I used this phrasing a little while ago, a couple lectures ago. So the optimistic scheme, in contrast to the pessimistic scheme, is you're basically going to assume that you're allowed to do the operation. And if it turns out you're not allowed, you sort of apologize and abort. In the pessimistic case, you basically first ask for approval to do the operation by acquiring locks. And then you're basically guaranteed that at commit time, you can actually commit. Okay. Any questions about optimistic concurrency control at this high level?
Just a question about the version numbers. How do they ensure that that there's like consistency across different objects, so that you're not reading one object and then like later reading another object, but a transaction modified some of those in between? Yeah,
well, that's a great question. And so let's. I think the way to get at that is we got to dive into actually figure 4, and which is, I think, sort of the core of this paper. So let's look at figure 4. And oops, not that one. All right, here's figure 4. We're going to spend quite a bit of time basically talking about figure 4. So the first thing, let's get this oriented in this figure 4. We see, let me actually get so we have a transaction coordinator, the C here, and then really the transaction coordinator is the application, and the application runs on the same machine as one of those 90 machines. But the way I'm going to think about it for the rest of this lecture is that it runs on a separate machine. I don't really care about it that much. Okay. And then there are different shards. In this case, there are 3 shards, 1, 2, and 3. And each shard is replicated twice. One's in the primary and one's in the backup. Then we'll see that this is the execution phase of the transaction. So the transaction has 2 phases. One is the execution phase, and then it's the commit phase. And during the execution phase, this is like where the transaction just runs. So does it begin? Does it read? For example, in this case, 3 objects are being read. One that was located, whose primary is in one object that is actually sitting in shard 1, one object that's sitting in shard 3, and one object that sits in shard 2. Okay, and we're region 2. And we can see actually, we look a little bit ahead. We'll see that the 2 of these objects are actually being written, and one of them is being read. So the object from number, shard 3, this is just a read operation, and these are write operations, or these are read operations, but those objects are going to be modified. So basically, as the transaction runs, it fetches objects from different machines, modifies them locally, and then, in the commit phase, the changes are being applied. And of course, the whole challenge here is that in the end, we want to achieve strict serializability. And in some ways, the protocol for at least writes almost follows like sort of very similar 2-phase commit protocols that we've seen in the past. There are differences in the details, but the basic strategy is the same. And we can sort of so let's assume that now we're done with the execution phase, so we're at the end of the transaction, and so the transaction is going to try to commit that transaction. There could be 2 outcomes. The transaction either successfully commits or it actually aborts. And it may abort because like some other transaction ran concurrently and modifies one of the objects that we either read or that we were trying to write. So the first thing, the protocol, the commit phase basically has 5 steps. The locking step, the validation step, the commit backup step, the commit primary, and then the truncate. Although the truncate basically runs almost lazily, and so it's not particularly important. Basically, so from our perspective, basically the point of interest of where things are stopping is here. So that's sort of where the end of the transaction is. Okay, so each of these objects, as I said before, when you read them, has a version number. So here's a version number. And they're modified, as I said, locally. Then at the point of this, so this is the commit point, where when the application calls and transaction, the protocol, this whole commit phase protocol kicks in. And so the first thing it does is what's called the locking step, step number 1. And the goal here in this step is to basically acquire locks on all the objects that are being written. And so we can see, based on this diagram, that apparently 2 objects are being written, namely this object, correct, because the context is the primary of shard 1 or region 1, and then this object is being read that is actually located on region 2, right? And apparently the third object that we read, from primary 3, is not being read because it doesn't participate in the locking phase. So in the locking phase, the arrows actually have all kinds of different meanings. So these dashed arrows are one-sided RDMAs. So those objects are being read with RDMAs. They're just fetched from the remote memory location and brought locally, to into the memory of the application or the coordinator. The solid ones are write RDMAs, and in this particular case, they append a lock entry to the log of the primary. So the primary has a log. Every primary has a log. So I'm just going to draw it like this, let me actually use a different color. So here we have the primary I with a log, and basically the coordinator, it's a commit record, or no, sorry, a lock record it's called, to the log. I'm going to make it a big record so I can write down what's in it. And in it is the version number of the time of the read, when the object is read. So that version number that came out here. That goes back into the log record, the object ID that's being read, and the new value for the object. And so this record is just appended, to the primary 1 and primary 2's log using a write RDMA. And so there's some thread sitting on those machines that looks at these logs and then actually does some operations. So in this particular case, if there's a thread sitting on the on P1 and P2 that monitors or spins or pulls this log and sees there's a new log record, and then in this particular case, what it will do, it will try to get the lock on the object that actually is listed in the transaction. So somewhere there's an object, and the object has some data in it, and it has this lock bit and the version number in it. And so P1 has one object that is being modified by the coordinator. P2 has another object that is modified by the coordinator, and basically the primary tries to acquire the lock on the object using a test and set instruction. And so it will try to set the lock bit using a test and set instruction. And if the log bit was 0 before, the log bit was 0 and it successfully set the bit to 1, then it knows that the primary knows that it actually acquired the lock. And in that case, it will send a one RDMA message back to append a message to the coordinator's message queue saying, okay, you successfully acquired locks for these particular objects. If the transaction, if the lock was already taken by another transaction, then at that particular point in time, the transaction is aborted. And so when the primary I tries to get the lock, finds out that the lock is already set using this test and set instruction, then that lock, so the try lock will fail. And the primary will add a message to the queue of the to the queue of the coordinator saying, like, I could not acquire the locks, and the coordinator in that case will abort the transactions. Any questions so far?
How are the locks obtained through Zookeeper?
No, these are there's other set of locks using Zookeeper. That's really for the configuration management, like the mapping of region number 2 primary and backups. These are just in-memory locks that the primary maintains. So in the address space, if we look a little bit back, correct? We look back at this picture. there was a region has objects. Every object has some data and a header. And in that header, there's basically a 64-bit number that where the top level bit is the lock bit and the 63 other bits for the version number.
What if the primary goes down? Does the backup have the same locks as the primary?
If the primary goes down, the whole what is going to happen is that there's a whole reconfiguration protocol happening and a new recovery protocol.
Oh.
The end result of that is that in this case, we hope that the transaction would be aborted, correct? Because it never made it to the end. We'll get to fault tolerance in a little while. So let's assume for I'm going to go talk about it in a couple boards, and I'll talk about fault tolerance.
Thank you.
So the version numbers are per object, right?
Sure, per object, yeah. Exactly. Okay, good. So,
Sorry, one more question.
Yeah.
Why do they choose to abort the transaction rather than blocking and waiting for the lock to be released?
Because they have read old material. They have not read the latest material value. And so the transaction has to abort.
Oh, I see. Because the lock means that it's going to change the next time.
Well, they ask for the locks after really written the object, right? So the coordinator modifies the object based on some version number, submits a bunch of writes, assuming that it's read the latest version number. And so by the time the commit starts to happening and you try to get the locks, and you discover that somebody else has the lock, that means somebody else already modifying it. And so that would violate serialization, right?
Yep, thank you.
So in fact, at the point you get the lock here, that's sort of the serialization point for write transactions. Okay, so at this point, the transaction has acquired all the locks for all the objects that is modified, so nobody else can actually modify them at this particular point in time. And so that's sort of the serialization point for the write part of the transaction. Make sense?
Yes, thank you.
Good. Okay, so now you might have thought like, why not do the same thing for read, correct? And get the lock for the read objects, get the lock for the objects that are read, check the version numbers, and you're in good shape. And the reason that that is actually in a separate phase, namely the validation phase, is to basically avoid these expensive write RDMAs, right? If you look at this vertical step, you'll see there's a write RDMA, then the server actually has to run something. It basically does the acquiring the locks, and then responds with another write RDMA. So here, this is a full RPC that actually requires server participation. And as we'll see in a second, to handle the read and the objects that have been read, the FaRM uses this validation step, and that validation step just uses one-sided RDMAs. And so there's no real server involvement necessary. Okay. So what happens on so we're basically at this point, where we're here, the transaction coordinator actually has the write locks. And now the only thing it does is it validates the read locks, or basically the read version numbers. And so it, for every object that is read but not modified, so in our particular example, that's only one object, correct? This is the one that actually is being read, the one at region 3. So it sends, it basically has a one-sided RDMA to read the version number, that 64-bit number, for the object that's being read. And when it gets it back, here, it checks two things. If the lock is taken, or so the lock bit is set, that means that some core, that a concurrent transaction is trying to modify it. So at that point, it just aborts. And so the whole transaction aborts again. If the version number is identical and it's not locked, that means that no other transaction is using it at this particular point in time, and the transaction can proceed. Basically, all the objects that are being read and modified have the version number at the start of the transaction, and nothing has changed yet, and so it is okay for the transaction to commit. This is really, the true serialization point. And since the transaction numbers are acquired at the beginning, or the version numbers are read at the beginning of the transaction, the transaction will commit in the order of the version numbers, basically, and they also will get basically strict serializability, because any transaction that will start after your transaction commits will have a higher version number, so therefore it also will commit later. Okay, so this is the point basically where the transaction coordinator says, at this point, we know that all the we have acquired the locks, we have verified, validated the version numbers for the read objects, and so this is basically the commit point, or the start of the commit point. So at this point, the transaction is going to say, okay, I'm going to go commit. I'm going to go commit. And there's multiple messages necessary in the commit point, as we'll see in a second, and those are mostly for fault tolerance reasons. And so at this point, namely, only the primary, has been only the primaries have been contacted of the objects that are being modified, but not the backups. And of course, we want to ensure that and write, once it commits, will survive F failures. Right? The system is designed to handle F+1 failures. In our particular design, there's one backup, and so it can only survive one failure. And so what happens in this final phase, the commit backup phase, is actually we're going to write to the logs of the primary, of the backups. So the backups have log. So here's backup I. Similarly, there's a log entry in it. And what we're going to do is write what's called the commit backup record. And the commit backup record exactly has the same information as the locking record that we saw earlier. So in it is going to be the version number, the OID, and the new value. Okay. And this is, like before, this is actually done using a write RDMA. Now, the backup doesn't really have to do any operation at this point. Like the server side of the backup doesn't really have to run anything. I just need, and so here's this trick where basically the sender waits on the acknowledgement of the NIC. And so this, this is not a one-sided or a write RDMA. This is just a NIC acknowledging that it got the right RDMA and that the right RDMA has been performed. And so that basically acknowledges, when we get this particular point in the protocol, the transaction coordinator knows the object is in the log of all the primaries, and the object's in the log of all the backups. And so now we're in a good position in terms of fault tolerance, correct? Because if any of one of the two fails, then the other one can actually apply the write operation. Then there's one more step that needs to be performed, and that is the commit primary. And we'll talk about it a little bit later in more detail. But this is the final step where there's one more log record written in the primary, namely a commit record. And the commit record just assesses the transaction ID that actually is being committed. And so like I didn't write that down in the other records, but every record has a transaction ID so that we know which transaction we're talking about. And again, this uses the same sort of strategy. There's a write RDMA to append to the log, and there's an acknowledgement. The NIC acknowledges the write RDMA, and so, but it doesn't require any interrupts, or the server itself is not being interfered with. Just the NIC is involved in these two operations. Then, as soon as one of the NICs acknowledges the commit record on one of the primaries, at that particular point in time, the transaction really truly committed. So this is the true commit point. The commit starts basically here, and this is actually the actual commit point. And at that particular point in time, the transaction coordinator informs the application, yes, your transaction has committed and is done. Then, of course, short point later, the logs need to be cleaned and shortened up and truncated and all the kind of stuff. And this is like the truncated phase. And that's basically piggybacked on later locking phases and validation phases. And so I'm not really going to talk about it at all, but basically it is to truncate the logs so that they don't grow unboundedly.
Sorry, but the hardware acts, they just go directly into the NIC of the coordinator?
Yeah, so let's go back to the RDMA picture, right? So if a write RDMA happens, so here's our write RDMA, the sender, the coordinator was running here, right? And here's maybe one of the primaries or the backups. And so the write RDMA goes in, writes maybe an entry into the log. The NIC does that. The NIC sends an acknowledgement back. And the coordinator will see that acknowledgement in the receive queue. And so as soon as the coordinator sees the ECK, for its write RDMA, it can proceed and knows that the write RDMA succeeded.
So does the write RDMAs only write to the log? They're
used in two cases. They're both used for these message queues and for the log append.
So when we say that a write RDMA has been performed, we mean that it has been appended to the log and not actually executed necessarily by the application.
That's correct. That's correct. So, for example, for the backup to actually perform the update to the object, it needs to read the log entry and then apply the update.
I see. And also for the lock bit for every object. So since everything resides in memory and we have like 64 bits for the version number plus the lock bit, so I'm assuming that it can fit in a single memory address, but we can still have the problem of, let's say, like the processor fetching that memory address into the register, and then maybe if we have like a multi-core machine, then another core fetching that like that same address, and then both of them flipping from 0 to 1. So, so I'm assuming that there's some support from the hardware there.
Yeah, so like as I mentioned a little bit earlier, the primary, when it acquires, so the primary is actually involved, correct? In the primary on the, so the coordinator sends, so in the lock step, like this step, correct? Step 1, the primary or the coordinator sends a write RDMA to the primaries, asking the primaries to lock the object. And the primaries answer explicitly with a message that reply. And so the crucial step that happens is that the primary, when it actually tries to get the lock, and that lock is set. This, the reason this is a one single 64-bit number is so that you can use a test and set instruction, which is atomic, to set the lock. So if two, so there's never the case. Like there's only if two test and set instructions run at exactly at the same time, one is going to win, the other is going to lose.
I see. Thank you.
And that's the crucial point, right?
I've got a question about the blue commit point.
Yeah.
Wouldn't it?
Let me maybe it's better to actually open a new slide with the picture again and just instead of scribbling even more over this, let me let's get one more picture so that we can talk about other scenarios. I'll make it a little bit bigger. I think we succeeded doing that. Okay, so you're worried about, let me see.
Yeah, the commit point between after step 2, but before step 3.
Yeah, so here, here's the decision, correct? Here we're starting to commit, and then basically here's the actual commit point, right?
Okay. Yeah, I guess I was trying to think about the scenario where wouldn't it be possible for a completely separate concurrent transaction that writes only P3 to get interleaved to like start and complete in that space? And then wouldn't that,
No,
would
when
that
in
be
the end,
problematic?
yeah, it would be problematic, but it can't, correct? Because when it writes, it has to get the lock at some point. And when we get the lock, we check the version number and the lock bit.
But does the read the P3 affect the version number in lock bit?
No, 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 it just gets the version number. But if like, okay, let me hold that question, because I'm going to come back at this.
Okay.
And then we'll see what actually happens.
All right, sounds good, thanks.
Any other questions?
This might be like a separate scenario, but what happens if, you know, after the execution phase, you know, it tries to acquire a lock and then crashes right after that, and the lock has been acquired, but no one else after that can acquire it?
Yeah, okay, so well, first of all, that machine disappears from the earth, correct? And the memory content is gone too. And the whole recovery protocol that is described in that next section in the paper kicks in. And that protocol in the end will abort that transaction. So that actually will get cleaned up.
Just another question. So here, like the coordinator is the client, right? Like it's the application.
Yeah, well, yeah, it is sort of.
And so the client is basically doing all the steps of like log, validate, commit.
Yeah. So you can think about the application is running on the same set of 90 machines, right? And you know, running this transaction, which apparently writes 2 objects and reads 1, and runs the protocol. And
so I guess what's confusing me is, so does the primary not communicate with the backup directly? It's the no, it's actually indeed the primary does not directly communicate with the backup. I see. Other than during the recovery protocol, there's all kinds of communication happening, but that's not shown here. So the coordinator just uses the configuration from the zookeeper. Yeah. Okay. So going back to this very first picture, and there's all kinds of stuff related to this too that I'm not talking about, like this precise membership and all that kind of thing. But basically, the zookeeper and the connection manager really decide, okay, well, this is the configuration, the current configuration we're running in. These are the regions, how they're mapped to primaries and backups, all that stuff. And if any failure happens, there's a whole reconfiguration process going on and recovery. I see. Thank you. Okay, maybe I'm going to skip the breakout room so that I can go a little bit further. The question, I wanted to answer the question that was asked in the post in the lecture, and I'm going to, as a lecture question, and I'm just going to do that by talking about an example transaction. And this also comes to this earlier question about, what happens, if 2 transactions run and it read 1 version and then it commits and blah, 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 all that stuff. So these are really, the topic here is, do we get strict serializability? And what I'm going to do is, like, I'm not going to give you proof, that we're getting strict serializability. Instead, what I'm going to do is I'm going to walk through 1 or 2 examples to build up some intuition. And hopefully that intuition, sort of convinces us, that things might actually be fine. So let's look at the following transaction. We have txn begin. And this transaction is, like in the beginning, it reads an object, adds 1, and then writes the object and commits or ends. Of course, commit might fail. So that's a transaction. And we want to ask ourselves, like, what are the legal outcomes, right? What are the outcomes that are correct?
So what are the possible outcomes of this transaction? What could be the state of, let's say X started at 0, and we're running 2 transactions, T1 and T2. What are the possible outcomes that are fine?
Either one of them could commit or both of them could commit.
Yeah, and so we can have X is 2, correct? If both commit. X is 1 is a possibility. If one commits and you want another abort, for example, they truly run concurrently or something. And any other possible outcomes?
0.
Yeah, 0 if basically both abort, correct? Maybe there's a crash. Okay, so those are the 3 legal outcomes. And so that's, you just have to make sure that is the case. So let's say T1 runs, and so it does a read operation. It gets X back, maybe at version 0. Same thing with T2. It reads, X is 0. And so it gets basically to run truly concurrent. And this is the question I think that sort of was asked in the lock, because we do a lock of X, we do a lock of X. And here's sort of the crucial step, correct? Because at this particular point, we're trying to get the locks on object 0, and can both succeed
in reading?
In getting this lock X.
Oh, and getting the lock? Not at the same time.
No, so one is going to succeed, correct? And so let's say the first one succeeds and gets the lock. That means it can commit, correct? So this guy will commit. And what happens with the second guy?
The second one, if it tries to obtain the lock at the same time that the first one is holding the lock, it'll abort and stop.
Yep.
If the first transaction goes through all the way and the lock is released, then it will obtain the lock and then check to see whether the version that it has for X is still correct. And it will find that the version has been changed, and then it will abort.
Yep. Yeah, good. That's exactly the two cases. So let me talk about the validation case in a second with a slightly different example to make it more interesting. But this is basically the outcome, correct? Good. And so even though these transactions in this particular picture ran exactly at the same time, they're actually getting ordered, and one wins and the other one loses. And that means that the other one that lost can run again. It will then read Rx is 1, and then hopefully succeed in the retry. Okay. Okay, so okay, let me do one example, and then I'll stop and I'll resume on Thursday. Actually, what time is it? It's 24. Let me actually just stop here, and then I'll do a second example that answers that earlier question on Thursday, and also talk about fault tolerance. I don't want to run too much over time. Anybody that has to go, please feel free to go. And I'll see you on Thursday. Anybody who would like to ask more questions, please feel free to stay, and I'll try the best to answer them. As you see, this is a complicated paper, and I'm glad that we're able to go in sort of depth, trying to really understand at least the protocol for normal operation. So with that, I just want to finish this lecture and either see you Thursday, or if you have any questions, please hang around.
I had two high-level questions. One was this whole hardware structure that they're using. Would it be useful at all if you're using it with pessimistic concurrency control?
Yes, I'm sure you can make the pessimistic concurrency control also better, because your RPCs are just cheaper, correct? But the real thing, and I haven't been able to point this out yet, but I was planning to, but I can do now, is if you look at the read-only transactions here. So read-only transactions. So if you're a transaction that basically only reads an object or multiple objects, what's the performance? How good is that? Like, how well is that going to perform?
Probably pretty well, since you only do the one-sided.
Yeah, correct. So if you look at the object that is stored at region 3, correct, which is the object that's being read, the only thing that happens is one-sided reads. Or one-sided RDMAs, correct? And there's no writes, nothing at all. So those because of the because the read operations don't require locks, there's nothing to be written. The only thing that needs to happen is this validation step, which also is a one-sided RDMA. So read-only transaction can just run with two one-sided RDMAs. And that's where the big win comes from. And the reason that that big win is there is because of the optimistic concurrency control. So I think basically to exploit RDMA sort of to its fullest, and I'm trying to make read-only transactions really, really fast. They went to optimistic concurrency control.
Okay, I see. That makes sense. And my other question was about like security. Is this thing, is it going to be secure if it's I guess someone already asked about this, but the part where the NIC just reads memory, it seems a little scary. So
yeah, it is totally scary, correct? And so there is some bunch of interaction between, you know, when the RDMA connection is set up, the operating system and the application. So the operating system won't allow, you know, the NIC to write to any arbitrary location. It will tell it, you know, here are the addresses, here's the VM virtual memory addresses that you can write to.
Okay, so you can make that production.
Yeah, okay. Exactly.
Okay.
Question about the performance.
Yeah.
So if you have, so the reads are quick because of the one-sided RDMAs.
Yep.
But if you have a lot of writes happening, like a lot of data in contention,
yeah,
that's still the case, or
no? Correct. Like what happens if you have contention? You know, actually, we saw this in this particular case, correct? If there's if we have a lot of contention, one of the transactions will abort. So this is really good for transactions that don't contend or not writing to the same records or same objects.
And even the reads, right?
Yeah, even the reads, right? Because the version numbers may change.
So what's like the main, I guess, use case for?
There's a lot of, you know, okay, so there's a lot of studies independent of this paper about pessimistic versus optimistic concurrency control. And, you know, clearly from the two benchmarks that they use in the paper, like TPCC and TATP, there's not a lot of conflicts. So the transactions are submitted maybe by different users or different clients, and they basically touch different tables.
So I have a question. If there's multiple clients doing transactions on the same object, how, so that they want to do a write RDMA, right, to the log.
Yep.
Is it possible that there will be like a conflict, like, you know, like one of them will write over the other log, or?
No. There's one log per pair.
One log per pair. Okay.
So this is exactly the reason why.
And then, when the transactions like time, is it like, you know, like to provide serializability, is it timed based on what?
On the version numbers.
Oh.
There's nothing like true time or anything like that here. Just logical numbers, like in same way as in lab 3, right, where you have logical sequence numbers for implementing your key value store. The version numbers basically play the same role.
Well, if two transactions got the same number, then only the one that got to the commit point first is going to get, okay.
Yeah, this is this case, right? One will abort, the other ones will succeed.
Okay.
If there's a message queue that is basically established between every pair, then how do you know? So then you'd have like multiple message queues for a given primary. How do you know which order to read those in? So you don't read them out of order.
you read all the messages from one source in the same order, correct? Because they're all going to be in one queue. So one source writes to one queue. Multiple machines might write, concurrently to different queues. You don't know what the order anyway is. So it couldn't affect the correctness of the protocol.
I see. So we don't rely on the orderings of the incoming concurrent messages.
That's correct. You just pull them in some order, and then you pull the queues in some order, and that's the word, that's the way they're going to be processed.
Got it. I also have one more specific question. There's a part where it says in the paper that it provides lock-free reads, which we've just talked about. But it also says it also provides locality hints, which enable programmers to correlate related objects on the same set of machines.
Yeah.
And I did not understand that, the latter part of the sentence.
Okay, so I have to look up the details what it is, but I think what it's referring to is that if your objects are all kinds in different regions, right? Like, let's look at this picture here, then you would have to talk to lots of different primaries, right? So if your object 1 is in this primary, object 2 is in this primary, and if you're touching if you're touching always a cluster of objects together, it would be nice if that cluster of objects is all at the same primary. So you only have to contact one primary instead of many.
I see. Thank you.
Any further questions?
So FaRM is not really suitable for long transactions, right? Because of the concurrency control.
Yeah, you're worried if long transactions that you get conflicts.
I mean, it also is assuming, I guess, read-only transactions, since we really optimize for them, right?
Yeah, absolutely. And many transactions, people have done studies, and you saw it in the Spanner paper too, correct? Where a large fraction of the transactions are read-only transactions. But that's clearly a property of the workload.
I think going back to my earlier question, I think I realized I was misunderstanding something basic about strict serializability.
Yeah.
Is it so strict? So okay, so here's a situation. Say there's one transaction that begins first that writes shard 1, shard 2, and reads shard 3. And so that begins first in time.
Okay, write object.
Yeah, 0. Write 0.
Write x at 0. Write y at 0.
And then read z.
Okay, read z. Yeah, at 0.
And then say there's this second transaction that begins after transaction 1 has started.
Yeah, like here.
Yeah, and it writes z.
So before it writes z, it must have read z, so?
Yeah.
And so it read z. What version number does it read?
The same one too.
Yep, exactly.
And then say it reads, then it tries to write z.
Yep.
And then say T2 commits before T1 commits.
Yes. Okay, so this commits. Yep.
And then T1 commits after T2 commits.
Oh, we'll try to commit, correct? And now we'll start doing this the whole lock validation, blah blah blah, correct? So before so what's going to happen, correct, is I was going to give you this example. This is actually an example that I'm saving for next lecture, but basically what happens, correct? Z will be going to get 1. At this point, the Z will be at version 1, correct? So the validation phase will run after the commit. That's what you said.
Right.
And so here's a validation of Z. And it has 0, correct? And then now it's 1, and this transaction will be abort.
Okay, so this is what I was wondering about then. So because after the validation phase passes, there's a period of time after the validation phase passes, a period of time passes, and then it commits. What if this validation happened before T2 committed, so it still saw the old version number?
It cannot happen because after the validation, after the commit has completed, correct? The commit backup, has recorded, and the primary have made the change. Before the application is returned, before the commit returns, Z has been updated.
Or I guess what I'm saying is, isn't it possible for T1's validation phase to happen before, or I guess maybe what I'm trying to say is, isn't it possible that T2's commit happens between T1's validate, happens after T1's validate, but before T1's commit?
Clearly, there's a risk, and it must be excluded. And is excluded. So you're worried. Let me just construct this case, and maybe I'll come back to you next week when we're going to talk about this anyway. But I think you're worried about. Let's see if we can get the picture back. So here's we did. So this guy committed. So he's basically doing the commit phase, correct? This is T1 or T2. What actually? What's this? T2. So T2 is here, correct? And then T1 is coming in before everything happens, before T2 is finishes, correct? So
right.
So like T1's validation also comes in here. So actually maybe okay. Let me rewrite it, and then we'll get back to you. Okay.
Okay. Okay. That's good.
That's exactly what I wanted to talk about.
Okay. All right. Thank you.
You're welcome.
So just to make sure, you're asking about T2 being like in between stage 2 and 3 of T1?
Yeah. Exactly.
But in that case, then T2, we could serialize it as T2 coming before T1, right?
Yep. So let's get back to this on Thursday. I have an example for that, and exactly where it's going to go over top of this.
Sorry, in the validation stage, you just read the version number.
Yeah.
Okay.
And serializability allows us to reorder transactions.
Yeah, but strict serializability not, correct? Like even if a transaction, strict serializability requires that if a transaction starts after somebody committed, that transaction is also committed after that transaction. Which is vertical, guaranteed because of the version numbers.
Got it. Thank you.
But strict serializability doesn't, if T2 ends, it's not enough for T1 to end after T2 ends. T1 had to have started, or maybe I need to think about this more, but yeah, I think this is what was tripping me up. It's like there's also a rule about when the transaction starts.
Yeah. Well, what happens in real life, right? When the transaction starts at some particular point in time, and basically, if T2 starts after T1 commits,
right?
So then it must be the case that T2 observes, T1's changes. That's strict serializability.
Right. But what happened if T2 starts and commits solely within? Then
it's a concurrent transaction, and either outcome is fine.
Okay.
Which I think is what the answer is for your question.
Yeah. Okay. I think that's what I was confused about.
Exactly. So
Okay.
when T2 starts before T1 commits, it's considered a concurrent transaction. And so T1 or T2 can observe it can either be ordered before or either after. Doesn't matter.
Okay. Thank you.
Which I think is also the answer to your example.
Right. Okay. Thank you.
Okay. We got it anyway already.
You're saying if T2 start is between the T1 start and commit, right?
And then it can be go for or after. Doesn't matter.
Okay, that makes sense. Oh, can I ask a logistics question?
Yes.
I remember in 6S0A1, you used to post these slides too.
Yes, I didn't do that here. You'd like them to be on the website?
I think slides are useful if you just need to look at the slides and you don't need to scroll through the video.
Okay, you're the first asking, so this is why I haven't done it.
Okay.
I'm happy to do it. I do save them all, and I know.
Thank you so much. Thank you. That was a fun lecture. Thanks.
You're welcome.